We have seen in the previous videos how to define directed and undirected graphs. Now we will define other interesting concepts on top of what we already know. Remember the definition of directed graph. Each edge has a direction. We can define a path as a sequence of consecutive edges. Consecutive means that the head of an edge in the path is the tail of the next edge. A cycle is a path that starts and ends with the same node. A loop can be defined as a cycle with only one edge. A directed acyclic graph, or DAG for short, is a directed graph with no cycles. We call a node a source if it only has outgoing edges. We call a node a sink if it only has incoming edges. A multigraph is a graph in which there could be more than one edge between two nodes. Multigraphs are used all the time in AI because they allow us to model different decisions that can be taken. A nice example of directed multigraphs comes from Choose Your Own Adventure books. These are books in which you choose the path you take by making certain decisions. The book would ask you to make a choice and then it would tell you which page to read next. In this case, the nodes in the graph are the sections in the book with their page number. And out of a node there are as many edges as the number of decisions possible. This is a directed acyclic graph because there are no cycles, you cannot get stuck. You will always reach an ending. There is only one source, that is page 1, the beginning of the book. There are multiple sinks, one for each possible ending, which could be good or bad. It is very common in AI to model decision-making problems where the nodes are the states and the edges are actions you can do. We need one more notion, the concept of labels, so that we can describe the cost of choosing a particular action. Labeled graphs are graphs that have some extra information, called labels, that are associated to each edge or to each node or both. In this simple example, we have associated to each edge one of the 3 symbols in the label set. It is very common to use labels to represent costs. For example, if nodes represent places and edges represents road, we could label each road with the expected travel time, or even with a distribution of travel times. Then we will give this data to a planning algorithm that is able to optimize the route. Here's another example of the same concept. Some of the coolest robots are the rovers sent to Mars by the Jet Propulsion Laboratory. JPL needs to solve a planning problem even before the rovers reach Mars. They need to plan the interplanetary path for the cruise ship. Because it is very expensive to launch interplanetary vehicles, it is essential to choose the best trajectory. A simplified version of the problem can be represented by a graph like this. Here, the nodes are planets, moons, or orbits, and the edges are the transfers that you can achieve. The edges are labeled by delta V, that is related to the fuel that you need to spend. This is all very simplified. For example, the relative positions of planets change every day, and these costs will change. However, this already gives a rough estimate of how big your launch vehicle should be. Postgraphs are another type of graphs that is very important for robotics. These are used all the time in SLAM, simultaneous localization and mapping. Usually, the noisy measurements from the sensors are used to create an initial postgraph. Then there is an optimization process that allows us to filter out the noise and create a map of the environment and of the robot trajectory. In a postgraph, each node is labeled with a pose, an element of SC3. Each edge is labeled with the transformation between the two poses. This is also an element of SC3. Because of the properties of SC3, if there is an edge from I to j with transformation delta ij, then there is an edge from j to I with transformation delta ji, which is the inverse of delta ij. Each node has a loop, which is equal to the identity. If there is an edge from I to j and one from j to k, there is also an edge from I to k, and the transformation is just the product of the transformations. There is an interesting property. The product of the transformations along a cycle is the identity. This property can be easily derived based on the actions we gave. Cycles can then be used as constraints in optimization. This is why closing the loop is so important in SLAM. Let's complete the formalization for SLAM. One usually has 2 types of edges in the post graph. There are ground truth labels, which we've been looking at, that are initially unknown. Then there are other edges that represent the noisy measurements. The goal of SLAM is then to find the value of the ground truth edges using the noisy measurements. Let's summarize what we've learned so far. We have seen undirected and directed graphs. Directed graphs have direction to the edges. Multigraphs add the possibility of having more than one edge between two nodes. Labeled graphs add the possibility of having extra information, called labels, associated to the edges or to the nodes. All these types of graphs are related. One way to see the relation is to see how we can project from the richer types to the less rich types of graphs. If you take a label-directed multigraph, you can forget the labels and obtain a directed multigraph. If you forget the number of edges, you can then obtain a regular directed graph. Forgetting the direction of the edges, you obtain an undirected graph. In the next videos, we'll see how to use these types of graphs for planning.